All right, so welcome to chapter 11 in cohort 3 of the ggplot book. Today we're going to be talking about color scales and legends. And it is a pretty long chapter, so I'm going to try to go through everything relatively quickly and then we can hop back and sort of look at stuff afterwards. Essentially what we're doing today is we're going to very briefly touch on the basics of color theory. Not so much color theory as a whole, but just like how do you encode colors? We're going to learn how to map different types of scales to colors in ggplot2, and we're going to learn how to reposition the legends on our plots. One thing I want to note before we start is that a lot of the functions that we'll be using are scale underscore fill underscore insert thing here. Um, we pretty much use the fill functions throughout the chapter, but there are also corresponding scale color functions. So anywhere you see fill, you can also substitute color. And there we go. All right, so color theory is um, something that we kind of learn about in school where you're like, okay, well, you got red, blue, and green, or red, blue, and yellow, sorry, with paints in elementary school. And you mix them together and you make other colors and you've got your complementary colors and all that stuff. But color theory is actually a lot more complex than that. And this is because the biology of the eye as well as the brain are complex. And this means that encoding color spaces, so sort of translating what the eye sees into something that can be written down in numbers, um, or hexadecimals or anything like that, can be really challenging. Because most human eyes have three color receptors, the most commonly known encoding for colors is red, green, and blue, which defines a color by the intensities of the red, green, and blue wavelengths. But one of the issues with this red, green, blue, or RGB encoding is that it's actually not perceptually uniform. So you can change a single unit on an RBG or RGB scale, and sometimes that will result in a very distinct color change, and sometimes it'll result in a very subtle color change. So it's not super intuitive. So in response to this, there have been a whole bunch of different attempts to encode colors, and one of the modern attempts is called HCL color space, and HCL stands for its three components. So hue is an angle that ranges from 0 to 360, and this essentially gives what we would call the color of the color. So it would, your values would represent blue, red, orange, yellow, purple, uh, whatever. If you've seen a color wheel, that is sort of, that's the angle part of it. It's going to be a wheel. Chroma is what you might think of as the purity of the color. So how vibrant or saturation of the color may be. So it can range from 0, which is a gray, to a maximum that will in and of itself vary with luminance. So for a set hue, depending on the luminance, you may have a higher or lower maximum of the chroma. And then luminance is the lightness of the color, ranging from 0, black, which is no light, to 1, white, or all of the light. So hue is an unordered character here, and then chroma and luminance are both ordered so that they actually have directionality, whereas hue, you wouldn't say like orange is bigger than blue or anything like that. So to sort of visualize HCL color space, what the authors provided us with was this graph that looks at uh, all of the HCL color space with hue mapped to angle, since it is an angular character. So sort of the angle here. Chroma is mapped to the radius. So the lower chroma is in the center, and then the higher chroma is towards the edges. And then for each slice, we have a constant luminance value. So this is a luminance value of 5 or very close to black, and this is a luminance value of 95 or very close to white. And so this is essentially visualizing, you can see our color wheel, but you can also see how the luminance is controlling our lightness, as well as how the shape of our space is not uniform. The actual shape of the space varies quite a bit depending on what area of the HCl space we're looking at. So it's a sort of weird polygon type thing going on. So there are a ton of resources out there for color theory. One that the authors recommend is this guide on color models. It includes a whole bunch of stuff on the evolution of color models, a bunch of different color systems that we are not even getting close to covering. If we have time, we could theoretically come back to this if people are interested, but I am not going to dwell on that at all for right now. One of the reasons why talking about color is super important in terms of data visualization is because there are differences in how different humans, who are our audience, perceive color. Most notably, many folks have color blindness, so that means that they are missing some of the receptors or cones that allow us to see different colors, and therefore their perception of color space is different than mine is, for example. It is therefore really important to consider how any visualization is going to look to folks with color blindness or people who might be using a grayscale interface, because these differences can make certain colors very difficult to tell apart. A very sort of simple baseline to use is to avoid any red and green contrast, because most color blindness is red-green color blindness. It is also a really good practice to check your plots with systems that simulate different forms of color blindness. There's a number listed in the available tools below there. And another way that you can help is by providing redundant mappings with other aesthetics like size, line type, or shape. So a common one here would be to have, if you had multiple regressions on the same plot, you would have each regression would be a different color, but you would also have a solid line, a dashed line, and a dotted line, for example. Some of the tools that you might use are online tools, like we have VizCheck, which is here. It simulates colorblind vision, and you can essentially sort of go through and run certain images, run different web pages, and it'll sort of simulate it for you with different types of color blindness. One thing that I recently learned about as well and wasn't mentioned in the book is if you use Firefox or a Firefox-based browser, it's maybe possible in other browsers, I'm just not 100% sure. There is also an inspect accessibility properties function. And if you click on that, one of the options is to simulate different types of either color blindness or even difficulties in perceiving contrast. And it will take that website, and that was a subtle change because there's not very many colors on this web page, but you can see the red, green, and blue change up there. I wonder if we can maybe, if we did sort of this web page, it might be a little bit more. Yeah, so you can see here with Protanopia, this figure appears very blue, whereas with none, it's very purple. So yeah, so that is a fun tool that I only recently discovered and have a lot of fun playing with. There are also a couple R packages that will provide simulations of color blindness. So dichromat and color blindness are both ones. Dichromat also provides a colorblind friendly color schemes that you can use in your visualizations. So just to do an example of the color blindness package, Here we've got, we're going to display 6 of the rainbow palette, 6 colors from the rainbow palette in all of the color blindness variations that it displays. We'll get a fun error because it appears that this might use an outdated version of ggplot. And what we'll see is that those 6 colors here, we can see our 6 sort of classic rainbow colors from base R under normal vision, deuteranopia, protanopia, and desaturation, so in grayscale. If we contrast that, we can use a more colorblind friendly color palette. Viridis is a really common one, which we'll talk about in a bit. And we can see using the display all colors function, we have a much easier time telling different colors apart here than we do with the rainbow colors above. So basically, when we're looking at color scales, we're going how the color scales function are going to be a little bit different depending on what type of variable it is that we're representing. So we're going to start off looking at continuous variables, but we'll also talk about discrete variables, binned variables, and date times and things like that. So with continuous color scales, color gradients are often used, and this is especially useful if you're showing like the height of a 2D surface. For this section and for some of the sections later, we'll be using an eruption plot from the Old Faithful data set, which I'm sure everybody here is quite familiar with at this point. So a really easy way to get started with your visualizations is to use some of the many hand-picked palettes that are available out there. These sort of take the guesswork out of making your or deciding your colors, spending hours and hours and hours picking the colors for your visualizations. While fun, sometimes is not the most practical use of your time. So ggplot2 supplies different scale functions that bundle pre-specified palettes. So ggplot2 takes some of the most popular palettes and sort of pre-bundles them for you. One of these is the Viridis color scale, which we just saw in the color blindness section, as well as 3 different functions that derive from the color brewer scales. We'll start off with the Viridis scales. They're basically designed to be perceptually uniform in color, but also when reduced to black and white, as well as to be perceptible for people with various forms of color blindness. So Viridis is usually like a very good start if you're just like, I just need a quick visualization. I need it to work for everybody or as many people as possibly. You can go with Viridis. So we have our eruption heat map for from the Old Faithful data set. This is the default. And when we apply the Viridis scale to it, we can see that the Viridis scale is sort of a nice like purpley to yellow. And let's see what these look like under different models of color blindness. In this case, it doesn't make too much of a difference, but you can definitely see that the loss of color. Ooh, contrast loss, that's fun. You can see that even though there are multiple colors represented here, the loss of having those color receptors doesn't really impact the interpretation under the Viridis. Viridis itself has a number of different palettes. So this is the magma palette, which operates under the same sort of base goals, but just, has different colors. For the color brewer scales, because of the way that colors function, depending on what sort of variable you're using, color brewer actually has 3 different functions that are useful for each of those different situations. So they have scale fill brewer, scale fill distiller, and scale fill fermenter. We'll kind of look at each of those throughout. Um, but scale fill distiller is the one that we'll be looking at here for continuous variables. So just the same as above, we take that eruption data set and we apply distiller. Distiller again has many different color options, and we'll look in a bit about, or we'll take a look in a bit at all of the different, the very many different color options that Color Brewer offers. So those are the packages that ggplot sort of pre-installs for you or gives you access to out of the box, but there are other packages that also have developed their own color palettes. So Psycho is one. It provides palettes that are both perceptually uniform as well as have been deemed suitable for scientific visualization. So this is Psycho's default. But as with any of them, they have a whole bunch of different options. Another really useful package is called Palettier. And Palettier is sort of unique in that it doesn't so much provide its own themes as it does allow a common interface to many other different packages with their own color palettes. So Palettier essentially allows you to use this scale fill Palettier call and then name both the package and the color palette from that package that you're looking to use and sort of put that in a uniform call. This can be really helpful if you're playing around with a visualization and you are not entirely sure which palette you want. So you want to sort of leave your options open. You can just have Palettier open, and then you can play around with changing between Vertus and Psycho and Color Brewer and all of those. So you can see here we go from Vertus to Psycho with the same command. I think I might mention it later, but I'll also call it out now. This one has scale fill Palettier C. The C stands for continuous. So there is a scale fill Palettier D, which is for discrete variables. So of course, you might not want to go with a hand-picked palette. You might want to make your own. You can absolutely do that. ggplot offers that functionality. And this sort of walks you through how to start to build your own color palettes. So for a continuous fill scale, the default is scale fill continuous, which in turn defaults to scale fill gradient. So I'm going to show you 3 different lines of code here, and you can see that they are all exactly the same. So if we plot erupt with absolutely no specifications, we get this. If we specify scale fill continuous, it looks exactly the same, as well as if we call scale fill gradient, because basically you've got erupt is defaulting to this, which is defaulting to this. So we've got like default inception going on here. You can make use of this gradient scale though to make any color scheme you like, depending on whether you want to specify 2 or more reference colors. There are different calls for that. So scale fill gradient, which is the one that we saw above, will produce a 2-color gradient where you basically specify the endpoints and then it'll interpolate between them. Scale fill gradient 2 produces a 3-color gradient where you specify the midpoint, and scale fill gradient n produces a gradient with n colors, so as many colors as you decide to put in. So we'll start with a 2-color gradient. We could specify this by specifying the low, so which color value will be for the low values, and high, so which will be the high values. So here we go from gray to brown, and all of this gradation is done by just a linear interpolation between those 2 colors. If we want to do a 3-point gradient, things get a little bit not more complicated, but there are a few more things that you have to remember. So you specify your low and your high point again. Apologies. So you specify your low and your high point, but you have to specify two different things for your midpoint. The first is what color you want your midpoint to be, as well as the value at which you want your midpoint to be. If you don't specify this midpoint, it will default to 0. So basically, it'll negative values will be the low, positive values will be the high, and mid will be 0. But that might not work for your data. You might want to pick maybe like a median value, for example. And then we can also do N colors. So here we're taking gradient N and specifying that we want the terrain colors and specifically 7 of them. So basically here our N is 7. And basically for this one, this sort of terrain colors, it has to be a vector of reference colors. It'll linearly interpolate between them. As we said, and I stopped trying to give me my notifications. The colors are going to be presumed to be equally spaced. So let's say you have values 1 through 7. It'll equally space them between them, but you can also supply a vector of values. So alongside this, you could do colors equals terrain colors, and then I think it would be values equals, and you can supply a vector there. So of course, if you're delving into making your own color palettes, you want to know how to make a good color palette. And what constitutes a good color palette is going to depend a lot on what you're trying to achieve and what you're actually what sort of scale you're using. So for example, if you're using a 2-point gradient, you are probably going to want to keep a constant hue and then just vary either chroma or luminance. On the other hand, if you're doing a 3-point gradient, you might want the perceptual impression of a natural midpoint, often 0. And there it can be really helpful to use contrasting colors. In the previous example, we saw white used as the midpoint, and then you had sort of more saturated bright colors as the high and low values. For specifying colors based off of the hue, chroma, and what they call value, the Munsell color system can be really easy. The book says that the Munsell color system uses HCl, but when I went to the Munsell package, it doesn't use a luminance value. It uses something called value, which is between 1 to 10, whereas luminance is from 1 or 0 to 1. I didn't have enough time to dig into how those are different, but I just want to note here that there might not be a very easy way to sort of directly sort of convert those two, or at least not that I know about. That said, you can still use the Munsell color packages. So yeah, you can see the color specification is a little bit different. You have this is your hue, the 5R basically is a way to specify a color. 5 is going to be your 1 to 10 integer for your value, and the 10 here is the chroma. Also, if you need very specific colors, you can use the color space package, which allows you to do some complex color work. Oh no, I have There we go. I wanted to open that in a new tab. So color space has just gobs uh, of information, and you can actually use HCl here, as well as it provides palettes. It's got a whole bunch of stuff. One thing that wasn't mentioned in the book, but that I really enjoy is there's a website called Coolers. I did it again. Go. And it is a tool that basically allows you to cycle through colors, lock the ones that you like, and then sort of figure out palettes from there. So you have a color generator, and its goal is that it tries to pick colors that are fun. So you hit the space bar, it gives you a color palette. Let's say I want to keep this magenta haze. And then if I cycle through, it will give me colors that it thinks looks good with the magenta haze. You can also select an image. Maybe you took a really beautiful sunset photo, and it will try to extract a color palette from the image. I have a friend who likes to do it with stills from like animated series that are really bright and colorful, and she'll use that for her like conference presentations as the color scheme. With continuous color scales, NAs will be something that you will probably want to account for. So you want to know what color is used for missing values. It defaults to gray. If you want your NAs to be invisible, you can set them to NA, or you can do NA value equals insert specific color here. So here, this is the default. You can see for where it is gray, that is our NA values. We can also make them invisible with NA, or if we want to make sure they're extremely apparent to us, we can choose something like yellow, which in this case contrasts quite a lot with the blue. With any sort of scale fill or scale color command, you can control the behavior of the color scales themselves using things that we've already been introduced to, like limits, breaks, and labels. You can also suppress things like breaks and labels by setting them to null. So if we've got our toy data frame here, we can look at our sort of default result. We can also, no, it doesn't want to. Okay, never mind. This is setting up our ggplot. This here, we're setting our limits. So you can see our limits here are actually quite a bit bigger than what is actually represented on the plot. So we never see this bright blue color. Alternatively, we can set our breaks to be in different spots. Or we can do something like making sure that our legend has dollar signs on the scales, things like that. So this is basically piggybacking off of a lot of the other functions that are used in legends, just here relating them to, in this case, the color bar. Speaking of legends, this is sort of our default. So this is, if you take a base plot, this is what you will get per legend. But using the guide color bar function, we can also change this. So we can take this color bar, which goes from 10 to like 45, and we can reverse it so that the lower values are on the top. We can also specify the height using real world units. So here we've specified that this is 2 centimeters and it is quite a bit smaller than in the previous examples. Or we can specify the direction. So taking our color bar and making it horizontal rather than the default of vertical, for example. Here we're doing this within the guides function. So we're going guides color equals guide color bar, and then whatever we want to do with the color bar. But we can also do this within the scale function as well. So here our first example is what we've already done where we reverse the color bar. But we can do that within the scale color continuous function. We can specify that we would like our guide to have a reversal. So these are the same thing, just using 2 different functions. Moving on, we have color scales for discrete values. As you might expect, these occur in a whole bunch of different situations. And a typical example is a bar chart, which is going to encode both position and fill to the same variable. The default scale for discrete colors is scale fill discrete, which in turn, sort of similar to how we had with continuous variables, defaults to scale fill hue. So once again, we've got, if we just plot bars, if we plot bars plus scale fill discrete, or if we plot bars plus scale fill hue, get identical plots. So next, the book sort of jumps back a little bit to color brewer, which apparently I can never say, color brewer scales. Here for discrete variables, this is color brewer rather than distiller or fermenter. These colors have in general been designed to work well in a wide variety of situations, although color brewer specifically focuses on maps. So they're usually good when they're displayed in large areas. As you can see here, I don't know what happened. I have to fix the font size maybe. As you can see, there are a ton of different options. And basically they're grouped here. So you've got sort of 3 discrete groups. The first group of palettes, they're all sequential scales. So they're very useful if you're using a discrete scale that's ordered. So something like rank data maybe, or this first group is also the group that will be used in color distiller for continuous data. If you have unordered categorical data, this sort of second group is usually the one you would want. Set 1 and dark 2 are quite good for points, whereas set 2, pastel 1, and pastel 2, as well as accent, are good for areas. Part of this is because of, I guess, the different perceptual needs of the brain while looking at points versus looking at larger areas. So here we can look at set 1 versus set 2, and they both look fine. These all look fine. But because scatter plots typically use small plot markers, something with really bright colors, like maybe set 1 up here, is going to be better than something with lighter colors like the accent palette here. So you can see here, set 1 versus set 2. Set 1 is a little bit easier to distinguish, especially against the ggplot default gray background. And the pastels, you can barely see the green points. So something to keep in mind. On the other hand, because bar plots usually contain really big patches of color, for some people, bright colors might be really overwhelming. And so you might want to use something a little bit more subtle here. And here we can contrast set 1, which is very preschool, with set 2, which is a little bit more sort of laid back, or pastel 1. And here, even though the green is sort of very similar to the gray, it doesn't pose as much of a visibility issue as it did with the scatter plot. As I mentioned earlier, if you want to use discrete scales with the Paletier package, you would use the call scale fill Paletier D for discrete, and then finish the call in the same way as you would with naming the package as well as the color palette. So first we'll talk a little bit here about defaults. So the default color scheme for ggplot, basically what it does is it takes that HCl color wheel and then it picks evenly spaced hues around there. This is generally fine for about 8 colors, but once you sort of push above 8, it can become really difficult to tell the different colors apart. If you need to, you can control the default HCl values with the HC and L arguments. So we can take our default chart here and we could change the chroma of every single thing or all of the colors by using the scale fill hue command and then picking here C equals 40. So we're picking a chroma value of 40 and it'll pick evenly spaced colors with that chroma value. We can also set a range of hues. So anytime you pick a hue, you have to specify 2 values. You have to have like the minimum of the hue value that you want and the maximum of the hue value, and it will select evenly spaced hues within that range. If you don't specify it, it'll do the entire range. What is really important to note about the ggplot default color scheme is that it is not inherently colorblind safe because it's not really taking perception into consideration. It's just algorithmically detecting colors. Another thing is that because the colors all have the same luminance and chroma, when you print them in black and white, they will generally appear as an identical shade of gray. So if you want a discrete color scale to be printed in black and white, if you already know you're doing that, or like you're submitting to a journal that makes you pay for color, which I don't think is as common these days, but does happen, you can use scale fill gray. If you want to, maybe you don't want this wide range of gray values, you can set the start and end points for your grays. So this is basically setting the luminance values for your grays. So here we want half black, half white, and white as our endpoints. Or if we want a perceptually dark chart, you can sort of go on the other end of the scale. And so here we're going from 0 to 0.5. If you want to set your colors manually, you can use scale fill manual for discrete scales. This is particularly useful if you want to choose colors that highlight a secondary grouping structure or draw attention to different comparisons. Maybe you're comparing a number of different treatments, but you want to highlight the treatment of the one that you're actually testing, not the one that you're testing because you're testing all of them, but the new treatment, for example, as opposed to like comparing it to the old standard treatment. So here you take your scale fill manual and then you'll supply the values. And here these are all just named color values. So you can see we've got different color scales. You can choose all grayscale if you want. One thing that is important to note is that if you supply just the values, it will go in order. So here it'll go from, it'll go gray as the first value, black as the second value, and then gray for the third and fourth values. If you want to maybe specify your colors without having to remember what order everything is in your data set, you can also use a name vector to specify colors as well as which level they are assigned to. And you can do that in any order that you want. So here we could use a named vector and we're going backwards here instead of going forward. So we're going DCBA, and you can see we get the same chart as above, even though we are specifying them in a different order. And I'm sorry, for some reason I can't see the chat. So if there's anything, oh, there we go.
I think we've just been chatting back and forth, just making notes as you talk. So I don't think there's any questions.
Fair enough, but yell at me if there's anything important. All right, so excellent. So for discrete values, as you would expect, we can control the limits, breaks, and labels. This is especially important if you have multiple charts, but maybe not all of your variables are present in all of the charts, but you want to make sure that your color scales are consistent. You can do that using the limits argument within the scale function or using the lims helper function. So let's say we've got two plots. We've got plots that are displaying the same sort of highway mileage stuff. One for 1999 and one for 2008. What we can see is that two things are happening here between these two. One, the axes are different. So you can see the y-axis, for example, goes to about 45 on the 99 chart and just shy of 40 on the 08 chart. The other thing is that because the default color scheme will just pick colors in order, here if we wanted to compare, for example, the P type of car, you can tell that I don't remember anything about these car data sets. If we want to compare P across the two charts, P is green in the first chart and it is blue in the second. So that is not ideal. So what we can do here is we can take the lims helper function. We can specify both our axis or our axes values so that we can make sure that they're consistent across our two charts. And we can lay out a vector list or a vector of colors, which can include colors that don't exist on our particular plot. So let's say we do that with the 99 chart. As you can see, it sets the axes to something that would make sense for our comparison. And then it also will display C and E, even though they're not in our chart. It'll just have them with no dot because they're that and alone and not there. And then we can compare them with this chart. It just facilitates the comparison. So that was using the lims helper function. So taking our ggplot and then doing plus lims, blah, blah, blah. In some cases, it might be more useful to customize arguments within the scale function itself rather than using the helper function. So this example sort of puts everything together and uses both the lims function to set our axes because we want our axes to be the same across both charts, as well as allowing us to set our color points. We've got our limits, and what we've done here, because we have fewer colors, is we've set our limits to make sure that all of the colors will stay consistent because they're in the same order. But we've also set our color breaks to get rid of the colors that we're not using. And in the second chart, because we're using all of the colors, we do not have to set the breaks. There's no need to, but we will still use labels to help people like me who cannot associate that P equals premium. So with legends, there's going to be two ways to customize them. The first is within the scale function, there is a guide argument. And the second is sort of similar to the previous example. We have a helper function guides, which will have a fill or color argument, and then you use guide legend within that argument. So it's a little bit sort of two steps removed. But we can start here. We have our base plot. It gives you this lovely default ggplot brightness. It gives us our number of cylinders. Let's say we don't want this in a single row. We want to add, or not a single row. We don't want this in a single column. We want it to be in a second column. We can do guides fill equals guide legend end call equals 2. That'll add a second column. So that'll add a second column here. So we get our nice little square. This column will default to going by column. So it will fill these, it'll fill all of column one first, then all of column 2. So here it goes a little bit unintuitively for an English, the English writing system, because it goes 4 down to 5, then up to 6, then down to 8. So if we wanted it to go by row, sort of following the English left to right system, we could do by row equals true, and it will go 4 over to 5 on the same row, down to 6 and over to 8. Once again, we saw this in the continuous variables. We can use reverse to reverse the order of the legend if we wanted our large values at the top in this case. So if we did our guide legend reverse equals true, we go from having 4, 5, 6, 8 to 8, 6, 5, 4. Something that might be useful in some cases, but is probably not in all, is using the override aesthetics argument to force the legend to appear differently from the plot. The big situation where this might be useful is if you are using transparency. So if you have an alpha value of less than 1 set, but you want to make sure that you're conveying the actual color or that your legend is actually visible, you can take something like this, which is making good use of the alpha value to show where there is overplotting, but unfortunately means that your legend is a little bit sort of dull. You can use override aesthetic to set the alpha to 1, and you can see that it turns the legend to be the sort of solid, fully saturated version of the color. Another thing that you can do is you can take the, you can use the key width and key height arguments along with the default units, so like 1 centimeters, 2 centimeters, to actually specify how big these keys are. So if you wanted bigger dots or smaller dots or whatever. So with binned color scales, the default is scale fill binned, which in turn defaults to scale fill steps. Any binned scale has a n breaks argument that controls the number of discrete color categories created by the scale. I think the default is 5, but I'm not 100% sure on that. I would need to double check. So here we've got scale fill binned and scale fill steps. They look identical because they're using default values. You can increase the number of breaks to give it more of a gradient appeal. Much like with scale fill gradient, there are ways to do multiple colors. So scale fill steps is going to be your equivalent to a 2-color gradient, whereas scale fill steps 2 is the 3-color variant, and scale fill steps n is the n-color scale gradient. So we can take something like our 2-color gradient here, add our white value for the midpoint with the 2 scale, or we can do very similar to what we did with the continuous values and use the terrain colors with 12 breaks in order to make a sort of fancier, larger gradient. Once again, for Color Brewer, there is a separate command for bin scales, and this is scale fill fermenter. So here's our fermenter call. One thing to note is that scale fill fermenter does not interpolate, so it doesn't do that linear interpolation that ggplot normally does. So if you attempt to do scale fill fermenter with more breaks than what that color palette actually has defined, you'll get a warning message and some of the colors won't be displayed. With binned variables, the limits, breaks, and labels are mostly the same as with continuous scales, but the breaks argument is defining the edges of bins rather than just the locations of tick marks. So you're actually performing a little bit more of a change there. With binned variables, the legend will use color steps rather than a color bar. This can be customized using the guide color steps function, which is very similar to the guide color bar function. So here we've got our default color bar, and it does not default to showing the minimum and maximum values. If you put show limits equals true, it will. The book also talks about setting the ticks and even steps arguments. I could not find anything in the documentation about the ticks argument, so I do not know how that works. And I tried even steps with this data set and it didn't seem to make a difference, but I would need to play further to see. It is in the documentation and it should work. It should, if you set it to false, it should not bin things evenly. But I couldn't get that to work with this particular example. So I'm gonna have to play with that a little bit more. One of the fun things with ggplot is the fact that it actually makes working with date times a little bit easier. So this translates to the color aesthetics where you actually have scale color date or scale color date time to work specifically with date times. These scales have date breaks and date labels that make it a little bit easier to work with these data. And I think it was last week we were talking about this, but you can set the breaks in sort of natural language values. So you can make your breaks 142 months for whatever ungodly reason. And then you can also set your labels using sort of standardized date time syntax for specifying whether you get abbreviated months or all of that good stuff. So it's really handy. I don't know if I would necessarily need to use it, but I could definitely see a lot of cases where somebody would. A little sort of brief dip into alpha scales was used. Basically, you can map the transparency of a shade to a value, and this is done using scale alpha, this is done using scale alpha continuous, which is the most common use of alpha mapping. So scale alpha is an alias for scale alpha continuous. In this example, we take that Old Faithful data set and just the more dense more dense that area of the plot is, the more the higher the alpha value is. They don't really go into a lot of detail on this. It's just like a, hey, did you know you could do this? And then the last thing they talked about is a little bit about controlling the legend position. So a lot of the legend control is going to happen in the theme function, which is covered in chapter 17. So they only really talked about a little bit about position and justification of legends here. So this is within the theme function. You can use the argument legend position. It takes the values right, left, top, bottom, or none, the last of which does no legend. And these work exactly as you would expect. They just control what side of the plot your legend appears on. So we've got left, right, on the bottom, and none. One thing that you'll note is that whether the legend defaults to vertical or horizontal will depend a little bit on which side of the plot it is on. But you can also control that directly. So you can use legend direction to switch between horizontal or vertical. Legend box will help you with arranging multiple legends, also horizontal, vertical. Legend box just looks at the justification of each legend within the overall bounding box for your plot. And one thing you can do is you can use legend position to actually place your legend within the plot space. So this will take a numeric vector of length 2, representing the sort of where your legend will start. Unfortunately, there's not a super easy way to do this. It will require trial and error to find a spot where you're not obscuring some of your data on the actual plot. So as an example here, we've got our base plot. We are going to set the legend position here, and this should be in the bottom corner, I think. Nope, top corner. This one's in the top corner. Yes, so it's at x0, y equals 1, so at the top of the y scale. We can set it in the very middle of the plot using 0.5s, or we can set it in the bottom right using 1 on the x and 0 on the y. So yeah, basically these will always range from 0 to 1, and you just kind of have to play with it in terms of what percentage of the x or y axis you want your plot to start at. All right, so I think that is it. Yep. And I finished 1 minute before the hour.
No, that's great. That was awesome. Yeah, I mean, this chapter, I mean, Gabby stepped out, so it's just you and I. Yeah, I think it's just like, well, I guess it depends on if it's continuous or if it's discrete, but like if it was discrete, I would always go back to like scale fill manual or scale color manual, which is not the best way to do it, obviously, for reasons of just sanity and being able to select a color palette that works, but also being accessible to as many people as possible. So, yeah, some of the other stuff I'm like, I don't know if I will ever use, like some of like the scale fill alpha and stuff. I'm like, don't know if I'll use that stuff, but everything else seemed pretty useful for some areas.
Yeah, it's definitely useful. I have like all of the resources they talked about open that I'm like, okay, I'm gonna use these later. I think color space in particular looks really neat, but I haven't had a chance to really dig into it other than to look at it to confirm that it does HCL, which is really useful because that is what ggplot uses. And they have a lot of like resources available on that website and everything. So I think that'll be useful.
Yeah, this color space thing is really cool. When you shared that, I opened it up and I was looking at it, and it was like, um, this looks really cool and very, very helpful, especially if you're trying to use HCL, like
Yes.
color mapping space, which that color theory stuff is like, like how do you represent colors and how do you represent colors in regards to how people perceive them? And it's like,
Yeah.
that's beyond me, beyond what I'm used to, of just like, hey, let's just select a palette and go with it. Yeah.
Yes. Yeah.
Um,
And then I was also thinking like I was reading a book recently, and it's about like different like how different animals like their other senses differ from humans. And you've got like like the mantis shrimp has something like 30 different color receptors in its eye. So it's like, oh God, it gets so much more complicated than this.
yeah, so then how do you represent that? It's just like, yeah, like I could totally understand why it's like a challenge because it's really hard to map perception into how a computer can translate it into
Hmm.
pixels and stuff. And the HCL helps, like that model kind of helps break it down, a little bit more than just like the basic color wheel we learned, but translating that into like how can I use this to you know make my own custom palettes and my own custom like color
Yeah.
mapping. You're just like, that gets a little hard, so I think I'm just going to go with like Beardus and just go with that.
Yeah.
So no, excellent job. I think this was excellent. It kind of cleared things up for me. I'm sure Gabby as well. And then yeah, this is cool. I have no questions, so
Awesome. Well, thank you for coming out.
yeah, hopefully